It is time for 1.6.3, where we do some applications. So most of these are going to be pretty straightforward mathematics. It's just the setup and the interpretation sometimes that can be a little trickier. All of these are pulled from the textbook, not from the homework problems, but above the homework problems. So if you want to search for these, you can get the text that way as well. We're going to read through these, and I'm going to take some pauses sometimes to like parse the information and kind of show you what is good practice for you when you're approaching your own application problems. So this one says it wants you, okay, so it starts by telling us what it wants us to do. It wants us to find the price-demand equation. Maybe don't know what that is right now, but let's just keep looking. It's already telling us what to do. We need a price-demand equation for a particular brand of toothpaste at a supermarket chain when the demand is 50 tubes per week. Okay, that's important. And at $235 per tube. So before we even continue reading, just a little quick explanation. So price-demand equation is just an equation that relates price and demand. The higher you charge, the lower the demand's going to be. The fewer people are going to buy it, right? But if I lower the price, then more people will buy it. That's what we're talking about here. And specifically, we're looking for this equation. If we know that a price of $2.35 is correlated with a demand of 50 tubes in a week of toothpaste at the supermarket chain. And the problem also gives us that the marginal price demand function for a lot of finance and economics and like business applications, a lot of times marginal is just kind of the same thing as derivative, more or less. So here we're assuming that the marginal price demand function, known as P prime of X, for X numbers of tubes per week, is given with this exponential formula. So again, this is a decaying formula. Exponential decay because it has a negative exponent. And then there's a part 2 of the question. So part 1 is find the equation. Part 2 is what should the price be if they want to sell 100 tubes in the week. So first we got to find P. So P is the antiderivative. P of X, right? If this is the marginal price demand function and marginal is the derivative of P, we need P. So it'll be the antiderivative of P prime, which is negative 0.015 e to the negative 0.001 x dx. We'll integrate this on the next page. Okay, so this is going to be equal to, well, we'll use a u substitution, and we can factor out a constant as well. I should have given myself more room. So with magic, I will. We're going to want u to be that exponent, 0.01x with a negative in front. So its derivative, just negative 0.01. So the du that we're looking for is just negative 0.01 times dx. Now this is a really good example of, depending on how good your math is, it might not be obvious what we need to do to that to get to that. And even myself, the work that I would use to force this to become that is probably just not worth the time. So I'm going to say, okay, dx is going to be du divided by negative 0.01. And let's substitute this now. So that tells us that the integral of negative 0.015, we could take that constant out if we wanted, times e to the u. We know that exponent is just u. And we know dx is du divided by negative 0.01. And now we can simplify and evaluate. So for example, the negatives cancel. And then we have those numbers, and the numbers can just come out in front of the integral. 0.015 divided by 0.01. We can use a calculator to help us simplify that. It's going to be 1.5. Dividing by 1/100th is the same as multiplying by 100, which is just moving this decimal place over twice. Integral of e to the u There we go. We're ready to go. And so we're going to get 1.5 e to the u plus a constant, or 1.5 e to the negative 0.01x plus a constant. This is not the end. It's not even the end of part 1. There are 2 parts. One, to find the price-demand equation, and then use it to answer a second question. I don't know what C is yet. And that's where this red stuff comes in. Demand is 50 tubes per week when the price is $2.35. Let's write that down. We have to use this to find out what C is. Because this over here is supposed to be the relationship between price and demand. Price is P, demand is X, remember. Another way of saying that is that the price at 52 should be $2.35. We can use this to solve for C. So if we do that, we get 2.35 equals 1.5 e to the negative 0.01 times x, which in this case is 52, plus C. Solve for C. If we do that, you have to be very careful. Actually, no, you don't have to be that careful. This is just a number. Take 235, subtract that number, and you'll get your answer. So 235 minus that number, what's that going to look like? 235 minus 1.5 times e raised to the negative 0.01 times 52. And you're going to get 1.4582. It makes sense to round to the nearest hundredth here because we're talking about dollars and cents. I'm going to give us a couple more decimal places though. So our relationship between demand and price is now going to be 1.5 e to the negative 0.01 rather, x plus c is 1.4582. Now, this question could be added to with a follow-up. I mean, there already is a follow-up, but there could be a middle follow-up. What price correlates with a demand of 0? Well, if nobody's buying this, the price is going to be, well, that's just when x is 0, be about $2.96. Apparently, no one's going to buy a tube of toothpaste here if they charge $2.96 for that tube. I'm pretty sure toothpaste is more expensive than this. I buy my toothpaste in bulk, so it's pretty cheap in general, but I don't know the cost of toothpaste. Been too long. All right, so let's do the end of this problem. If they sell 100 tubes per week, what should they set the price at? Well, if demand is 100, what is P going to be? Let's find out. We're just going to plug that in. Plug in 100. Get 1.5 e raised to the negative 0.1 times 100 plus our constant, which was 1.4582. $2.01. Maybe we just do $1.99. Then we can really be like a supermarket. But this is the math answer. And again, for applications in general, especially business applications, the math is like a guideline, and then you use what you know about the real world to make your decisions. So in reality, if they did want to do this, they probably would just do $1.99, $1.95, or whatever they thought was best. They probably would not charge $2.01. but that's the mathematical answer. All right, so that's this first problem. Next one's going to be problem 1.42 in the book. And that says, suppose the rate of growth of a bacteria in a petri dish is given by Q of t is just 3 raised to the tth power, where t is given in hours and Q of t is given in thousands of bacteria per hour. Remember, Q is a rate here. Q is a rate, so the units of Q should be units for a rate. Thousands of bacteria per hour. Q is a rate. Maybe write that down. It's a rate. If a culture starts with 10,000 bacteria, that's going to be useful. Find a function big Q of t. Remember, it's pretty normal that if the rate of change is the little lowercase, then the antiderivative will be the uppercase. We've seen this with little f and big F before. It gives the number of bacteria in the petri dish at any time t. How many bacteria are in the dish after 2 hours? So again, 2 questions. We'll do them just like before. So we know that Q of t is going to be the total number of bacteria. And what do we know about the net change theorem? That the total bacteria is just going to be the antiderivative. Well, actually, the net change theorem says it's going to be the initial plus the antiderivative, which is another way that you could approach this. But yeah, we're going to need the antiderivative of little q with respect to t. So we need to anti-differentiate 3 to the t. And usually this is an e. But it doesn't have to be, remember? Remember our formula all the way back at the beginning. We can find the antiderivative of any exponential function. All we have to do is divide by the natural log. Oh dear. I'll have to go back and make a note on that one. All we have to do is divide by the natural log of a. All right. So, and in the case when a is just e, these become the exact same formulas because the natural log of e is just 1. So it becomes this upper formula. All right. So where were we? Oh, yes. So the antiderivative here is just going to be 3 to the t divided by the natural log of the base. The base is 3. And then we use the starting value of 10,000 to solve for c. We know that initially there are 10,000 bacteria. What's wrong with what I wrote down? There's a mistake with this. See if you can find it. The culture starts with 10,000 bacteria, so that looks right, no? Look at our units. Q is given in thousands of bacteria per hour, which means that big Q is in thousands of bacteria. Very easy mistake to make. So Q of 0 is actually 10. When you plug that all in, you're going to get something a little interesting. You're going to get 10 is 3 to the 0 divided by the natural log of 3 plus c. C is not equal to 10 here. Be very careful about this. So when we have this, we're going to get that c is just 10 minus 1 over the natural log of 3. And as a side note, there is a c that is 10 here. And that's why the net change theorem is not broken, but it's a different c. You know how I say that, you know, if we have 2 c's, we just combine them to 1 c. If we subtract a c, we just write it as plus c. If we multiply a c by 2, well, it's still just some constant. And that's exactly what's going on here in this formula. This c is not the original c. And the original c would be like 10, but we just write it as a plus c anyway. And that's why it looks kind of funky like this. For an application, we're going to get an approximation. 10 minus 1 over the natural log of 3 is something. It's going to be about 9.0898. 9.0898. And that'll give us our formula. The number of bacteria after T hours in the thousands of bacteria is going to be 3 to the T divided by ln of 3 plus C, which is 9.0898. And you might say, why did you approximate this instead of that and not that? Well, that's a good question. It'd be fine either way. Well, actually, the original C would be 9, I think, not 10. Anyway, our C is about 9 point whatever. Okay. And so that's the first part. That's the formula for the bacteria. And specifically, we are asked about how many bacteria are there after 2 hours. Well, that's going to be Q of 2. It's going to be 3 squared over ln 3 plus 9. Type that into a calculator. 3 squared over ln 3 plus this new number, 9.0898. That should be subtraction. And that should be a plus. No negative bacteria here. 17.282. Or about 17,282 bacteria. All right, so again, one of the big things with a lot of these application problems is really make sure that that you know what units you're supposed to be using here. And as a side note, again, one of the advantages of application problems is if you do mess up, sometimes you can figure it out. We don't have negative bacteria. I typed in the equation wrong. It should be a plus. Something to watch out for. And one of the advantages to this sort of problem. Last one, which is pretty similar. I'd recommend you try this on your own, pause the video, and then we'll do it together. So this says we have a population of fruit flies, and this population increases at a rate of g of t is 2e to the point of another exponential function, and it increases at that many flies per day. So again, this is a rate. And not thousands this time, just 1-to-1 units. That's great. If the initial population is 100 flies, okay, that's going to be useful. How many flies are there after 10 days? We're going to approach this just like we did before. The g of t, number of flies, is just going to be the antiderivative. 2e to the 0.02t. Take the antiderivative with a u substitution. I'm going to skip a couple steps that I have confidence that you guys can do. And we're going to get 2 divided by 0.02. E, oh, now I'm getting nervous. Shouldn't skip steps, Jason. We'll check our answer. Oh, that's the wrong button. Anyway, and then we have to solve for C. We know that G of 0, initially, right, there were 100 flies. We'll use that. 100, well, we can simplify this. All right, if we simplify that, that's 100. 2 divided by a 50th is 2 times 50. That's 100. So 100 is equal to 100 e to the 0 when you multiply it all out plus c. You're going to get that c is equal to 0 here, which feels weird, but it works out. Because if c is equal to 0, right, what do we have? We have that g of t is just 100 e to the 0.02t. And again, you can see that this is the initial value here, not the plus c. All right, and it wants us to know how many are there after 10 days. Just plug in 10. like so. And let's see how many flies there's going to be. Too many. That's probably, oops, probably going to be the answer. All right, so what we have is 100 times e raised to the 0.02 times 10. Oops, the times 10 needs to be up here. We're going to get about 122 flies. All right, let me know if you have any questions, and good luck.